the introduction. Let me start just by before I get into the technical content. Let me say, good. I'll introduce myself because my journey is like, as Don said, I did a postdoc at Berkeley from 2007 to 2009 with Mike Jordan, which was fantastic. My back during my PhD, what I worked on was machine learning. Deep learning didn't exist then, and for natural language processing. So back when none of this stuff really worked. And then around the time I left Berkeley, I started as a professor at Edinburgh. I started working on kind of machine learning for program synthesis, kind of code generation, and software engineering problems. These were very exciting to us at the time, but this is when we were just starting to get deep learning, so kind of none of this worked. And then I moved to Google in 2018. And it's only kind of very recently, and kind of when I've been at Google, I've been working on machine learning for code generation. And then kind of very recently, like in the past year, I've started to get interested in AI for security. So why am I telling you this? There's kind of three reasons. One is I always like to begin a lecture by professing my ignorance. So my background is very much more on the deep learning side than on the computer security side. So you're very welcome to ask me any questions you want about computer security, because fortunately Dawn Song is sitting in the front row, and we can get and many of her group as well. So we can get kind of expert answers to a lot of these questions, even if I don't know them. The other thing is just like I like to give career advice. I have a blog where I give people kind of defunct career advice and research, and because it's fun. The one thing when I look back is that I mean, your career is very long, right? If you see like in the past couple of years, like things are febrile, everything's changing every 3 months. It's not the technologies that are on top now. They're not going to be on top in 5 years. They might not be on top in 5 weeks, the way things are. So like having kind of just like change is normal. Technologies change, and you want to learn how to change with them. And the other thing that I think is a theme of this talk, and something that I liked in the course, is kind of like thinking across different disciplines, right? So if you are working in machine learning, if you're working sometimes applied research or product-driven research, or if you're in tech building products, a lot of there's going to be the kind of machine learning tech, and there's also going to be the problem that you're trying to solve. And if you know only the machine learning part of it, and you don't think about kind of deeply about what problem you're trying to see, you're kind of missing a trick. Like the more you understand the kind of AI for computer security, the more you understand about computer security. Or if you're building a product, the more you understand about what your customers want, it'll help you to do better technical work. Okay, so that's the end of my sermon. And now I will start actually talking about kind of coding agents. So there's going to be 3 parts. I'll say a little bit kind of in general about kind of agents for code, like SWE-Bench, SWE-Agent type things. That'll be the first part of the talk. Then I'll start talking about AI and agents for computer security. And then at the end, I'll talk a little bit about a project that Dawn mentioned that I'm part of with a number of other people to do LLM agents for finding security bugs. And but I'm going to start off with being maybe a little bit philosophical about what LLM agents are, since you're already partway through the class and you've already seen a number of examples of agents. I wanted to give, like, LLM agent is a bit of a buzzword. So I wanted to give kind of my perspective on kind of what that buzzword means. Other people would say potentially different things, and that's okay. But this is kind of what I would emphasize in terms of what seems kind of fundamental. So I would say this slide's a little bit abstract. I'll start talking about actual stuff in a few minutes in one more slide. But for me, if you ask me to define what an LLM agent is without the kind of buzzword bullshit, whatever, I would say, look, it's a multi-turn LLM with tools, right? The mental thing is kind of this React loop that we're going to talk about. And what makes this fundamental? Like, why is this good? One is that you get dynamic computation time. So the point of, like, if you just prompt an LLM question answer, it has to start generating the answer right away. And maybe some of the earlier tokens kind of commit the LLM to an answer that it then has to that it doesn't want to contradict. Whereas if you give it kind of dynamic computation, if you give it, if the LLM can generate a thought, whether it's kind of a reasoning model or whether it's just prompted, that gives more computation time for harder problems. The other thing, which we're going to talk a lot about, is kind of information from external tools. And that's kind of another part of the point of agents, is that you can actually, is that, for example, in coding agents, you actually run the code, see what happens, and then write different code based on the output. And it turns out that's incredibly powerful for kind of more complex code generation tasks. And we'll see examples of lots of other things you'd want to use external tools for in kind of code generation, software engineering type scenarios. The other thing that's maybe more from the kind of cognitive perspective of what's interesting about tool use is that tools give the agent the ability to test hypotheses, right? So the agent can, like in the thinking part of a loop, say, oh, I think that when I run this code on this input, it will break at line 13, and they can actually do it, see if it was right, and then kind of revise in later turns, like say something different if it turns out that this hypothesis was wrong. And then I think that's something we're kind of, for some of these simpler tasks, you might not need that level of experimentation in the agent, but I think for more complex tasks, you will. And then the final thing this gives you, which I think is really good, is like if you want the LLM to actually do anything, right, then it needs to interact with the external world. And that's, in one sense, that's what a tool is giving you. So I guess, so the main thing, maybe I disagree with what I wrote on the slides next. So you could think of when people talk about planning or chain of thought, you can view these as like special cases of dynamic computation type, right? These are ways to use the extra computation that you get from having thinking tokens. This de-emphasizes multi-agent a little bit. That's, maybe that'll turn out to be really important to have different interacting agents with different prompts, but I think my sense is that that's still emerging. The jury is still out on that. Okay, so that is, so that's going to be the end of the philosophy for now. I'll intersperse philosophy maybe into the rest of the lecture. I'm going to start by not talking about agents, though. I guess I've already started by not talking about agents. I'm going to continue starting the agents lecture by not talking about agents. And the next thing that's not agents that I'm going to talk about is evaluation. So, the reason that I'm doing that will become kind of, I'll talk about that in a minute. Before, when we first started to see but I want to talk a little bit first about, say, the prehistory of evaluating code generation in LLMs. So when we start, there was a big kind of moment in, I guess, 4 years ago now. It doesn't feel that long, but it was, when we kind of saw a step change in the ability of LLMs to do code completion and code generation tasks. This was about the time the OpenAI Codex model came out, kind of the GPT-3 kind of iterations. And at that time, there were a couple of kind of evaluations of kind of code generation capabilities that people were doing at the time. And BPP that we did at Google, and kind of human eval from OpenAI. And these are kind of broadly similar things. And what these are is basically natural language to code. So each of these data sets would have, order of several hundred examples where you would generate a small Python program, 5 or 10 lines of code. And you wanted to do that given like a 1 or 2 sentence prompt that says what the code is supposed to do and a series of assertions. And at the time, this was, at the time that this came out, like, I'll say more later, and these were both kind of generated by people. So there were kind of human annotators kind of wrote the programs and the problem descriptions. So I don't recommend using these evaluations anymore. They're kind of more like MNIST. But I think they let me talk about a couple of points. That's why I'm starting with this. And at the time that these came out, it was kind of amazing that a language model could generate, an entire function of 10 lines of code, right? That's not amazing anymore. So one thing that's interesting about this I'll come back to later is I want to talk about kind of both how you would use these to do evaluations and why you don't use them anymore. So we talk about how you use them to do evaluations. So what we would do for these data sets is we measure passive K. So how often, given the kind of natural language prompt, do we get a correct answer in K samples? So if we go, if you like my fancy AI generated graphic there, if you take a prompt and get, say, K samples from the model and just say, kind of run them all on those, a set of assertions that maybe the model ones that model did see, maybe a few hidden ones the model didn't see, and then say, okay, how often does the program pass those assertions? And then if any of them pass, you get a score of 1 for pass at K for this example. So the reason I'm telling you this is there's some principles of this that even though we don't use MPPP human eval anymore, you probably shouldn't, there's some principles of this that you do want to use when you define evals. One is that this requires an automated correctness check to work. Having that, if it's at all possible for you to have that when you're defining an eval, you want to have that. The other thing that's kind of nice about this, you don't see this as much in agents because it's so much more expensive to run, is that you get to measure kind of explore exploit behavior if you can afford to do a pass a K eval. Right. So if you had a model that like always produced the correct answer, it was either always right or always wrong, and there was no diversity in its output, it's kind of pass at 1 would be the same as pass at K. Whereas like, if pass at K kind of goes up sharply, that's telling you, well, maybe the model's first solution isn't always correct, but it's giving you more diversity. That's kind of interesting. The other thing to point out here is kind of an interesting question, like, does pass at K match what you want when you deploy the model? And the answer is sometimes yes and sometimes no. If you are doing code completion, you probably don't care as much about pass at K, because I'm not going to show every time I hit the completion button, you get to see 10 examples and pick the one that's right. That's probably not so good. Whereas if you're doing something more agentic, it might be fine. It might be perfectly fair to say, I mean, it is perfectly fair to say, oh, in production, I'm going to generate case samples, keep the ones that pass the test cases, and only show, say, a highly ranked one of them to the user. So sometimes this is kind of reasonable. Sometimes it's a good metric. Sometimes it's not. So it's always interesting to think about for this particular way in which I'm evaluating a coding tool. Does it match the way I'm actually going to use it in production? Okay, this is maybe not, I just putting this because I think it's cool. It's a little statistical aside, which you may or may not know. And since like machine learning used to be based on statistics, you see less of that work anymore. I find it kind of interesting. If you are, so how do you want to compute, like, say I care about pass at 10, right? How am I going to compute that? Well, the naive thing you could do is I could say, well, take 100 samples from the model and say, okay, what percentage of them actually passed? So maybe it's 20%. And then what I want to know is if I take 10 samples from this, how much does it, how likely I'm to get it? And so you can take 20% and plug it into that. It turns out that's bad. That's a really noisy statistical estimate. So it turns out it's much better to say, take those 10 samples and then say, if I take those 100 samples and say, if I take a subsample of 10 without replacement, right? How often do I get at least one success? And that's the estimator that's proposed in the Codex paper where they talk about human eval. I don't know, I just think that's cool. Okay, so now so I've gone through this at length, and the reason that I've gone through this is to get to this slide. Which is like, what is the design of a good evaluation for coding agents or for agents in general? And in 2021, I think these were probably reasonable evals at the time. And there were kind of 3, and the reason is that they could drive model development. The reason is the reason they could is that they were kind of just hard enough. So they're not at floor, they're not at ceiling, so that when you improve the base model, you would actually see a difference in these numbers. And then at the time, they kind of weren't leaked. Right, so they weren't already on the internet. Now, probably not, right? They're kind of too easy. It's kind of too easy to you could overfit to the assertions, and they're certainly leaked. So these are probably more like the MNIST of code evals now. But the reason I go through this is when we look at other evals, we can ask kind of the same question. So the probably most influential so far, so let's now move to evaluations kind of used for agents. So the most influential evaluation has been SWE-Bench. So let me kind of talk, which I didn't, maybe I have the citation on a different slide, but it's easy to find. So what SWE-Bench is a way of kind of it's a data set of real world coding problems that have been collected from Python repositories on GitHub. So one example of an example from the data set is here. So the idea is that they would I talk about filtering on the next step. So the idea is you would have a problem statement, which is actually from kind of the statement from the GitHub issue tracker. This is one thing I point out here is just kind of the issues will often contain kind of pointers to a part of the code or that you want to modify. And all of these examples have test cases that were a part of the patch. And there's cases for which before the patch, the test case fails, and after the patch, the test case succeeds. So you have, for each of these, you have kind of a test case, you have an issue description, you have a change to the tests, and you have a patch. And so the goal of the SWE-Bench is generate the patch from the generate the patch from the description. And these are okay, so I've talked about, so there's some steps of filtering you do, like this fail to pass filtering, and also the fact that you can actually install and run the projects. And I wanted to show in terms of looking at the domain. So this has been kind of very influential because at the time that it was introduced, it was kind of at the Goldilocks level, that the kind of baseline LLMs were getting like 2 or 3%. And then as soon as we switched to agents, we got kind of non-trivial boost. So this was kind of introduced, it was an interesting subset of real world tasks that was introduced just at the right time where this could drive model development. And so it's kind of been very influential and a lot of people have used it. What I would point out from the things on the bottom is on the left is a kind of a pie chart of which 12 projects these came from. And you can see there's kind of like, it's kind of a small set of domains, right? These are Python packages that are kind of, mathematical data analysis, web, right? So there's kind of a, it's not covering the full range of software engineering tasks, but it is covering tasks that are interesting. And to look at the set of files edited, the set of functions edited, it's kind of a big step above previous evals, but there's a lot, again, that it's not covering. So there's also, and then there's also a kind of a small, so one thing that's both kind of nice and not nice about this is that you have the issue descriptions that are coming, the issue descriptions are the ones coming from GitHub. So that means that, sometimes these are underspecified, or there are test cases that are just they're tangled. Somebody was fixing something in the code, they wrote some more tests, but it doesn't actually test the problem. So there's a subset where these have been removed. So now let me pop up and say, okay, now let's ask the same question that we asked of the previous slide, which is, are these evals good? And the answer is, well, yes and no, right? So as we said, this is a significant step up in realism, and it came at the right time to drive the field, so that's great. What's wrong with it? There are lots of things that are wrong with it. That's okay. There are lots of things that are wrong with everything. So what's wrong here is that, you can overfit to the test, right? The tests aren't an exact verifier, so you can produce a patch that makes the test pass, but isn't actually correct. Maybe even something worries me a little bit more is the natural language is out of domain, in the sense that if you are interacting with an agent in your IDE and you want to tell it to make a change, you're probably not going to use the same types of natural language as you would in a GitHub issue description, right? Like maybe you've diagnosed the problem a little bit more if you're going to share it with other people than if you're just asking an AI in your IDE, please fix this. And some issues might contain things about the solution, right? About what part of the code the issue should be fixed. Sometimes you know that, sometimes you not. And so we've talked about coverage a bit already, and we've talked data leakage is, when this data set came out, a lot of people were kind of worried about, oh, these are all from GitHub. This is in the training set of all the large models. Should we be worried about that? And I think the answer is when systems are getting 2% on SWE-Bench, no, we should not be worried about that. When systems are getting 50%, we probably should. And then the other thing, whenever you do these kinds of historical data sets, I think something that people often don't realize is these commits are tangled. It's kind of often the case on open source repositories that a commit will not just fix the one issue that it claims to fix, but it'll do some other things. Like maybe it fixes another issue, maybe it does some other cleanup, right? So that kind of affects the quality it certainly affects the test cases, but it also affects, like if you were going to do supervised fine tuning on patches, that might not be such, there's problems with that. Okay, so the reason I'm going through this at such length is that I think in large part, the quality of either the base LLM or the agent that you develop is going to be driven by the quality of the evaluation. And the reason for this is, I don't know, sometimes I like making analogies to statistical machine learning methods. Any kind of organization that builds either LLMs or LLM applications, it's just doing giant combinatorial optimization, right? So you have a design space, you have a bunch of knobs, like we'll talk about the knobs for agents in a minute, and you are, and you say, okay, what if I set this knob this way? What if I add this tool? What if I change the system instruction this way? What if I clean up, this part of the post-training mixture? And then you try it and you see how the numbers change. So if your numbers aren't good, you're hill climbing on the wrong thing. And I think that has a direct impact on whether the quality of your evaluations has a direct impact on the final system, whether it does what you want. And so the things you want to think about are like, some obvious, like, I think the main one is essentially the level of difficulty. You have to be in the sweet spot. Also, you want things that are realistic, that test what you care about, and that aren't leaked to be leaked. And the other thing, like all evaluations have a shelf life, right? Like once they start out, they start out like with, say, MBPP human eval, they start out being kind of hard and unleaked, and then like a couple of years later, they're easy and leaked. So it's just like you have to keep making new ones continuously. Okay, so I hopefully I've spent enough time. So I'm kind of going into kind of technically simple stuff at length, but I think it is important to actually building these things. So now I can actually kind of talk about Code Agent, which is kind of a good thing to do in a lecture on coding agents. And one that I thought was kind of a particular milestone was SWE-Agent. So this was kind of one of the early ones that was kind of specifically designed for SWE-Bench style tasks. In some sense, this talk is going to be very repetitive because I think that we're all working with the same set of 3 or 4 ideas, right? In the kind of the base models or in the kind of, application layer on top of it, which an agent is an example of this, like Crank. And there's a certain thing, like if you want to do an agent for, I don't know, fixing AV issues versus an agent for kind of making patches to repositories, it's going to be a lot of the same types of engineering that you do. First thing you're going to do is define an eval. The second thing you're going to do is kind of create something that looks like SWE-Agent. So what SWE-Agent is, it combines like a bunch of different things that kind of, people had all done kind of before, but it's kind of a powerful combination. So one is that it's going to give you that we're going to instruct the model in such a way that it does kind of chain of thought in the sense that it explains what it's going to do before it does it. There's going to be a set of tools that are specific software developed, and the agent is going to get execution feedback. So that way, like I've said before, if you have you can get information about what happens. So the main loop, which is going to be kind of what I call the React loop, and I put those emoji on there for a reason. React loop from the React paper a couple of years ago. Oh, because I think this kind of loop is kind of at the heart of what we're saying about agents, of kind of this idea of kind of chain of thought plus tool use. So all you're doing is basically like a very simple loop where you say at every point you have what we call a trajectory, right? Some text that the LLM has generated so far. At every step, we ask the LLM to generate more text. And then that text will end in a tool call in whatever format that you like. And then you get the tool call, you actually run it. Every tool is basically, to a first approximation, a Python function that outputs more text. Like, I'm not going to talk about multimodal agents because we don't really need them for code. There's been less work on multimodal agents for code so far. Um, and then whatever the output is, you just append it to trajectory and then you repeat, right? And that's it. So the and this kind of loop, we'll talk about alternatives to this kind of control flow as well, but that loop alone is kind of very powerful. It's at the heart of a lot of what these things are doing. And in principle, the LLM can generate whatever text that it wants, right? We would hope that it's something that actually helps it decide what tool call to use. And so we instruct it, as a system instruction in the beginning. I guess I should have initialized this with what we call like a system instruction. And that's going to tell you, that says it, please explain what you're doing. And so then it will. So one of the main design decisions here is like, well, what tools do you want to use? One option that you could imagine is, okay, we'll just give the agent access to a Linux shell and an IDE. Then a person can do on that machine, it can write whatever code it wants. This seems, I'm not saying this will be true forever. Right now, this still feels a little bit futuristic, right? 2 weeks from now, who knows, right? But and this is kind of another theme when we talk about the design of agents. Maybe this is one of the things I forgot to write on the slides, is that the design of the agent harness and the tools, you have to co-design it with whatever the model can do, right? So if you're doing prompt optimization to try to decide, okay, how do I summarize the output of this tool? Well, probably the way you're doing it is you're adapting either knowingly, or if you're part of or unknowingly, you're adapting to whatever the model has seen in post-training data, right? Because the closer, like you want whatever format to use to be things the model's familiar with. So where we are now is like, okay, maybe right now option one is a bit ambitious. So let's do something different. Let's make things easier for the model. So what we'll do is we'll say we'll design tools in such a way that there's going to be a small number of them that are kind of good for this task, and they'll have inputs and outputs that are friendly to the agent. And there's kind of a really catchy term they use in the SWE-Agent paper. This is like an agent computer interface instead of a user interface. So instead of HCI, there could be a science of ACI. That might be going a bit far, but there are design principles here. So what are they doing in SWE-Agent? Okay, yeah. Before I get to that, so like I said, a tool is just a Python function or a code that the agent can call and to get a string from the context. What do you want these things to do is when you're thinking about them, well, they should be easy to describe to the agent, right? So you don't want to like make up technical terms, right? That like if you're when you're designing a piece of software, you can invent vocabulary, right? Different objects in the thing. Here, like you want like the closer I've heard this, I think some of the guys I think I heard this from some of the people who developed Copilot is so there's a lot in the initial, probably still, but certainly in the initial version of Copilot, there's some really clever prompt engineering to make things work with the LLM of that time. I'm sure there still is. And one thing they talked about, they call it like the Little Red Riding Hood principle, right? That when you're doing prompt engineering, you want to kind of lead the model down familiar paths from post-training data. And I think that's true here as well, that you want kind of to be able to describe what the tool does in a way that the agent will have understood. That like there are plenty of web pages that talk about jump to this line of code, right? So that's something that's natural. The other thing is you want you want the actions to be compact, right? Like you don't want something where the agent has to call 4 or 5 tools to do one logical thing. The other thing is you design the output of the tools, right? So you might say, it might make a difference. Oh, how do you handle trailing new lines in the output of some tool? Or if the output, if you're doing a code browser tool and there are many, many results, like how do you summarize that? Like there's different options. And the other thing you want to think about is guardrails is like state. So like if you're talking about code editing, right, then You could imagine something where say the agent adds, the first thing the agent does is add a stupid syntax error to some file and it doesn't realize it. And so then the rest of the trajectory, the agent is just messed up because no matter what it does, it hasn't fixed the syntax error, right? So you want to kind of try to have some error checking to avoid, especially for like stateful tools like code editing, getting the agent into a bad state that's easy to get out of. Okay, so what tools do they have in SWE-Agent? One is, well, I think they did have a Linux shell, but that's maybe sometimes useful, but not so useful. But often like these tools are helpful. I would say there's like three types of tools you could think about in kind of agent, in this style of agent. One would be kind of information gathering. So that doesn't help the agent solve it gathers information, right? So in the case of code, this would be kind of doing code search and kind of viewing code files. So you can, so this would be, and so you see some of the design like this would be things like, oh, find this term in this file, find this term in any file in this directory. You notice that it's kind of a nice shortcut, right? You could imagine having just doing ls in the Linux shell and then doing, then the agent could do search file in any of these. That seems cumbersome, right? And then, how do you deal with files that are too long for context? Here, what you can do is call the open to see part of a file and then have a specific kind of scroll commands. So the second kind of thing you can do is acting, right? Which is just in this case, make edits or create new files. And then you can get feedback by saying, okay, I'm done. Please submit this patch. So, and I think in general, if you want more complex tools, I think most tools will kind of fit in to some kind of, to fit into this. There are guardrails here that like, if you make a dumb edit, that kind of syntax error, or lender error, it just gets rolled back for you. And you can do, there's things like this. So, I mean, give you a sense of kind of what I couldn't fit a full, I will show some trajectories throughout this. I couldn't fit a full SWE-Agent trajectory on here. But here's kind of an example of the kind of explanations you might get, right? That you say, okay, oh, now I know what to do. We need to add a check to ensure that all of these things are the same. Let's edit the code. And so it says, oh, replace these lines of code with this. Or if you want to do like kind of file search, you might, perhaps you want to, you might like lead the lines, you might provide line numbers. Like these are kind of like, you need the line numbers so that you can use them in a subsequent command. So you can design the tools to kind of fit together in this way. Typically what you will see for this agent, you would typically see the tools are called in the order that you would expect. Like if there's some identifiers used in the issue description, then the agent can call the code browser tools to find kind of code that's relevant to it. At some point, one of these thoughts will say, oh, let me make this change. And you see edits, and then you might see like kind of multiple edits and then a submit. But the agent is restricted to do that, right? This is just, as far as the model is concerned, there is just a string, and the model is continually appending to this string. Okay, so let me say, I'll say a little bit about the results and the SWE-Bench data. So the first thing is I did kind of set it up and say, well, SWE-Bench was really hard when it came out. And so if you look at, whatever the state-of-the-art LLMs at that time and say what percentage of the, I think, couple thousand issues in SWE-Bench were resolved by the model, it's like 1 or 3%. And I can tell a kind of fun, I don't know if it's fun for me, I don't know if it's fun for you, story there, which is that when SWE-Bench first came out, I thought it was a pointless evaluation because it was just too hard, right? Like, how do you hill climb on a model when you're getting 1 or 3%? So it turns out I was wrong. And the reason that I was wrong about that is because agents are actually really good. So like when you put an agent loop on top of these base models, you go from like 1% to 12%, right? And I think now, now the state of the art in full SWE-Bench is quite a bit higher than that. So it was, so it's like the fact that agents came out, SWE-Bench came out as part of the reason the kind of part of the code development that happened. The one thing to point out is you might, one thing I can kind of experimentally criticize here, although I think there's a good paper, the results are good, is an agent is going to have to generate more tokens, right, to get this kind of same level of performance. So you see that is represented as the dollar average cost per successful trajectory in the second column. So the fact, you would like to know, you would like to see computation normalized results. Like it would be interesting. Like if I ran 10 times as much, do I expect to, if I ran 10 times as many, if I generate the same number of tokens on average from both, here, I think agents work, it's fine. But I think when you're comparing other changes to the agent, you might say, well, there might be some changes to the agent that look really good, but it turns out what you're doing is getting higher, like maybe you add, I don't know, some kind of grep tool that puts lots of tokens in the environment. And if it helps, that's great. But it might be that, oh, it's helping because it's adding more tokens to the average trajectory. And if you didn't have the tool and just generated more trajectories, you could get the same point on the kind of cost performance curve. So it's something, you want to think about that when you're running these comparisons. There was something that I wanted to say about the shell only agent, which I don't remember. Oh, well, okay. Maybe we'll come back later. Okay, so that's kind of maybe the first kind of very dynamic React style agent. So now I want to talk about a different kind of agent design, and that's kind of the other extreme, which is called agentless. It's kind of like, so this was kind of like in terms of like, this is the other extreme in terms of how much control flow do you handwrite? So what we've talked about is kind of dynamic, where the control flow is I'm appending to a string. Everything else the LLM decides. The LLM could in principle implement whatever algorithm it wants on top of these tools. The other extreme is just procedural. So basically, I will write some, say, Python code that does something natural for solving program repair tasks. And every time where it's kind of like where I might say, oh, okay, so first I'm going to iterate through every file in the project, and then I'm going to whether that file is relevant to the issue description or whatever. And so whenever you get to a point in the algorithm where you need to say, quote unquote, magic happens, you call the LLM. And so this basically, like, you have code, you have the logics in code, but then you're asking the LLM to make to make certain decisions in the middle of the control flow. So that's basically what Agentless is doing. So so there's kind of three, I say hard coded, I don't mean that in a pejorative way, kind of three steps. One is like, figure out what you want to edit, then generate a patch, and then validate the patch. And I will give you a colorful diagram that says the same thing. So what you're going to do is you'll have this workflow where at various points you call an LLM. So you'll start by saying, okay, you have some code base, you textify the structure of the repository, you prompt the model to say, oh, which file should I look at? So then the model will give you a list of kind of top end files, and then each of those you could say, okay, here is a skeleton of the kind of methods and classes within each of those files. Then you call the LLM again to say, oh, where does it look like I should edit? And then you can do that one more time to get a set of lines that you might want to edit. So at each one, so at every point you have kind of an n-best list of potential things that you might want to edit. And then you go through and say, okay, now for each one of these, let me independently give this to an LLM and say, hey, here's the description of the issue, generate a patch. And then what you can do is, and then once you have that, you apply the patch. Hey, let me see which ones pass. Now, one thing that's kind of important about SWE-Agent is you don't know what the test cases are, right? So the agent itself has to come up with its own tests that hopefully describe the issue. All the agent has is it has the previous tests, which probably don't test the bug it's trying to fix, because if they did, the test would fail and the bug wouldn't be there. So the agent's going to have to propose its own tests and then run the tests and the proposed patches. And so that gives you a set of patches that are kind of plausible. that in the sense, it's a technical term, it means that they pass the agent-generated test case, and and then we kind of rank them, and then one of them we submit. So okay, so there's a very big table. So at the that I'm not going to read the entire table to you. This is a subset of the SWE-Bench leaderboard at the time that the paper came out. The order is now changed. But at the time that this came out, this was one of the best open source agents, and it still is. The order is slightly different, but it's still kind of near the top. So what I want to so the thing I want to take away from this is what are the advantages and disadvantages of different agent designs. So under one, the more dynamic SWE-Agent type approach, the LLM gets to choose what problem solving strategy it's using. So, if the LLM, if the model produces a patch that's nearly right, and then there is one of the tests fail, then you can extend that trajectory. The model can decide, oh, do I need to do some more code search in order to figure out, oh, that this thing has failed, why I wasn't able to get the patch right, or maybe I just want to make a small change to the patch that's going to make it correct, right? The model has this has the flexibility to decide what strategy it's going to do. Whereas on the other side, for the more procedural one, if you have a case where the problem can be solved with a simple workflow, then why make the LLM figure out what the workflow is, right? And let the model spend more time actually trying to solve the problem, and you kind of avoid tool use errors because the tool use is happening on top of the LLM rather than within the LLM. And you can avoid things where the LLM makes some initial mistake and then the whole trajectory goes off the rails. So what was it? I missed one thing there. Okay, yeah. So a lot of these come down to how do you want to budget the amount of compute that you have at test time. Like if you imagine that I have one kind of partial patch where it's failed, is it a better idea to kind of extend that trajectory and try to fix that patch? Or is it a better idea to throw it away and generate a new one, right? Agentless is more going to be like generate and test, whereas dynamic could choose. And the second part of this is that this may be a case where the kind of winner between the two of these depends on what type of what's the word? Depends on what type of problem you're considering, right? So for simpler, smaller patches, generate and test might be better. I'm speculating here, but perhaps for longer, more complex changes, we will start to see, as we move to that, we will start to see more advantages to having more flexibility in the problem solving side. So you think there's kind of a continuum in terms of, we've actually talked about 3 different coding agents so far. One, which I didn't talk much about, was just give the agent a Linux prompt. So that's kind of there's almost all the control is in the model. Or you could do something like SWE-Agent or Agentless, and there's kind of a continuum here. And it may be that has the base model capability changes, has the amount of, and it has the complexity of the task, changes the design point here that you might want to change. Okay, so there are, I think, 3 more kind of coding agents I wanted to talk about. But these kind of go faster and faster because they are kind of more similar to each other. Another one of the kind of highest performing open source agents right now is this one, AutoCodeRover, which is from this University of Singapore. There's I think the last time I checked, I think it was OpenHands was the biggest, was the highest on the SWE-Bench leaderboard. That might have changed. But I think there's a lecture from last semester on that, so I won't go into it. So for AutoCodeRover, the 2 things I wanted to talk about here are, the first one is that it has a different set of search tools. So it's that rather than being, oh, let me find this string in a set of files, it's actually indexing the methods and classes in the files in the same way that an IDE would. So you can have the search tools are things like, find a class with this name, find a method with this name in this class. So that kind of changes the type of code browsing behavior you see. It can do kind of more explicit command click. I also wanted to talk about the kind of control loop here, which is that it's sort of a concatenation of dynamic agents. So there are two phases to this. One is kind of try to collect kind of information gathering, try to do code retrieval, and then the second part of it is actually generate the patch. And each one of these a separate trajectory with a different system instruction, a kind of different set of tools, and then you run them one after the other. So it is kind of like it's kind of an in-between point between agentless and SWE-Agent with kind of some procedural control, some that's more dynamic. And the other thing that you get from having these two agent loops is kind of information hiding. Like if there were if in like one, for code search, this probably doesn't matter so much, but there might be other types of agents you design where you care about this, which is that if you have you might want one of these kind of agent loops to come up with an answer, and then you want to throw away the intermediate reasoning. Just get the answer that it came up with and give that to another agent loop. That's something you could, because you're worried that if you keep irrelevant things in the context, it will confuse things. So let me, I think I have two. So I didn't want, okay, well, that's fine. So the other, no, I'm going to do things out of order. The one, I will come back to those. So you can take this, you could take this kind of procedural control to another extreme and say, rather than do filtering, you can have a state machine. So this, so repair agent is another kind of recent one where, it's a similar these are for kind of program repair tasks, a different data set. It's not SWE-Bench, but that's not so important. The kind of main thing is for doing program fixing is the design of the agents given by the state machine. So where, we kind of design what are the steps that we think you do when you investigate and repair a bug. Each state has a kind of specific system instruction that says, please try to understand the bug if you're in this state. And depending on which tool the model does next at the end, and then the model's then given the system instruction, the model's going to do some thinking, output a tool call. Depending on which tool call is chosen, you move to a different state of the state machine. So if you're currently in the collect information state, then when you do a code search, you stay in that state and you can do more code searching. If you call the kind of write fix, that's a tool that moves you into a different state and changes your system instruction. So that's kind of a different way to get dynamic control with more information hiding. Okay, so the final thing I wanted to talk about, which is, although there are, so what I've been talking about are more kind of academic agents. Although there are a lot of industrial coding agents, there's less technical detail about them. So this is one of the ones that I know that's kind of like a research agent moving towards being used in industry. So this is kind of a research agent at Google called Passerine. And these are kind of several of, so I'm not involved in this work. Several of my friends in the kind of developer tools org built this. And so this is an agent that is designed to solve kind of coding issues that Google developers have. And what makes the Google code base kind of different, and is that everything is in a mono repo. So this thing is rather gigantic, and therefore we have kind of the build system has to take into account the fact that there's a mono repo that's so big that we can't kind of store all of Google's code on our laptops, for example. So I've talked about agents. So the first thing you have to do is kind of make an evaluation if you want to have this kind of thing. So what they did is there's kind of a SWE-Bench-like loop where instead of using GitHub pull requests, we use kind of internal bugs and fixes from our issue tracker system. So we'll take cases where there are bugs that were fixed and kind of some heuristics that these are kind of reasonable things that we want to use for an agent, like there's a change in tests and the kind of size of the patch and so on. And then we do a list of filtering to have kind of a curated test set, both of two different kinds of bugs. One is ones where the bug report was written by a person, but it had a kind of a small enough patch size and so on. And the other one is kind of automatically generated bugs. So these are things that I'm going to talk about this a bit more in the computer security part of the lecture, is that that when we're doing testing of Google code, sometimes we will run sanitizers. So these are kind of dynamic analyzers that kind of sit underneath the code that's running and check that certain bad things aren't happening. So one bad thing that could happen is a buffer overflow. So there's a particular sanitizer called address sanitizer, which you can use it you can use it at home as well, where it tries to detect at runtime whether your executable is reading or writing out of bounds, and if it does, it causes a crash. So internally, when these kinds of bugs happen, it creates automatically a report in our issue tracking system. So we have a number of reports like this, and so this research agent is kind of a React style dynamic agent like SWE-Bench, SWE-Agent. The difference is the tools are actually our Google development tools. So there's an API to kind of Google code search, our build system, which is called Bazel, and is kind of and you can kind of view and edit files. So that's kind of Passerine. And one thing I wanted to point out, since I've talked about evals, is what are the differences between this curated evaluation set and say SWE-Bench. So these top three plots are kind of different. They are cumulative distribution functions of different statistics of SWE-Bench versus our internal evaluation for Passerine. And so SWE-Bench is the blue one, and then the other two are kind of the machine or human subset. So generally what it is, especially so this one is like how many identifiers are in the patch, how many files, how many lines. And so, for example, especially the human patches from this data set kind of are larger, affect more files, kind of have more identifiers than what we see on SWE-Bench. SWE-Bench is more similar to these kind of sanitizer reports. And then there's also maybe I won't get into reports about you can look into how this agent performs. Okay, so that is so that's going to be this is maybe a good place to stop for the coding agents part of it. So I'll get into AI for security next. But the main thing so I've talked about how agents drive the design of these systems, evaluations drive the design of these systems. The other thing is like all of these are kind of more similar than they are different. I think we're all working on the same three ideas right now. So and the other thing about these is the ideas. I mean, I don't mean this disparagingly. The ideas behind all of these agents are fairly simple. It's just the design space is large. So there's kind of a large set of hill climbing that you do when you have this. So we talk about, what is the design space? So one is, okay, which tools do you want? We've seen different examples of that. How do you handle control flow? Is it dynamic? Is there a state machine? Do you kind of recursively call an agent within a lower level agent, like, whatever, right? Do you just write the control flow in code? And then there is kind of the design of the text, like what do you write in the system instruction? You can do kind of the general things you do for prompt tuning. You can tell the agent in kind of stronger or less strong language how you want it to solve the problem, what order you want it to call the tools, how you describe the tools, how you summarize tool outputs, and so on. All of these things have to have sandboxes, right? Because you're running model generated code. So I guess there's kind of a right way to do that, but that's something you have to deal with. If you want to have an agent that is communicating with external surfaces, right? All of these are hermetic, right? If you were doing something like, to presage the next set of the talk, like penetration testing as an agent, then you need to figure out, oh, this is actually communicating with external, or if you wanted an agent to manage your email, right? Like how would you have to think about, okay, how do you even kind of prototype that when you have to communicate with external surfaces? And one thing we haven't talked about, because these are research agents, is, what do we do? How would you involve a human in the loop? Like when do you ask for clarification questions? When do you ask for approval? Okay, so I already talked about this. So that is kind of what I wanted to say about kind of general coding agents. So the next part of the lecture is going to be more kind of AI for computer security, and then some of our own work in AI security. So now I want to kind of finish by talking a little bit about AI for computer security, which is kind of like maybe a more emerging area than AI for code generation. Um, why did, was this? Oh, no, I didn't see that. Sorry, I'm confusing myself. Let me start. I'm going to kind of dive in and talk about, I'll talk about evaluations, but for particular, um, I want to start, like, one type of work that I want to start by talking about is kind of capture the flag competition. So that's one. So if you say, oh, I want to do AI for security, if you start by saying, hey, I want to do AI for computer security, questions are, okay, what problem do you want to try to solve within that? And how do you, um, so there is a particular type of competition that people have, like at schools and security conferences, things like that, which are called Capture the Flag. What I like about these, at least as a stepping stone, is that it gives some idea of the breadth of the type of real problems that you'd like to solve in AI for security. So that's why I think it's interesting to talk about. There's different kinds of CTF competitions, and I am probably going to kind of butcher this description a little bit. So I would feel free if you are a computer security expert in the audience. But the idea is there are different types of tasks that are like toy versions of something that you might do as a professional researcher, and that the task is set up in such a way that for this particular type of Jeopardy task, where there's a special message which I call a flag, and if you do the task for a while, you will see something where you're like, oh yeah, that's the flag, like, hey, I'm the flag or whatever. Maybe it's not that, but and then you solve the task and you can submit it. So like one example would be, like, there are kinds that are like digital forensics, where they might say, okay, here's a file system, find the hidden message, or they might give you more hints about what it is, and then you have to know, okay, how do I kind of look through this file system, do clever searches, maybe more complex ones, I might need to do steganography, or I might need to like find a QR code or whatever. So this would be more like kind of modeling digital investigations. Then there's like the ones that are just cryptography, where you have an encrypted message, you want to decrypt it. There are ones where you want to kind of pwn challenges, you want to exploit kind of memory vulnerabilities. You might want to kind of find a vulnerability and get a surface. There are ones where you want to kind of identify vulnerabilities, or the web ones where you want to do kind of injection or kind of cross-site scripting attacks. And the the reason I like to go through this is two. One is you can kind of see how these map, even though these are kind of games in some sense, you can see how they map to kind of real world tasks that you might want an agent to do. And the other thing that's nice is, I think if you've been sitting in this class or even just in this lecture, by the end of this, I think if I just took one of those and gave like a random one of these to like any of you and said, design an LLM agent for this, you could do it, right? It's pretty obvious why you would want an agent to do any one of these tasks. So, I mean, again, like we were saying for coding, like a kind of toy game benchmark isn't the same. It's not as complex, has a real world task. But I think if you can't do these, you're probably not going to be able to do the real world tasks either. So, and I think we're currently at the stage of agent development where kind of CDF tasks are still a challenge. So there are kind of several different data sets, like some of them are kind of recent, with kind of historical CTF competitions of different difficulties. So like this top one, the NYU one is maybe the most recent one. There's also one with from kind of high school level competitions. And each one of these will contain kind of the task description, kind of sandboxing environment, and a rater that will automatically check like whether you found the flag or not. So that gives you something to start with. And I want to go through kind of one recent paper to show, okay, how would you use an agent for one of these tasks? So this one called Enigma is going to be the last, maybe the second to last agent I'm going to show you. They do all run together after a while. So what this is, an agent to solve these capture the flag competitions. So it is a React style loop. So here's an example. And do I see on the next slide? Yes, I do. So this is just an example of running some of the tools, like you can edit files and so on. So the types of tools that you have, there are the kind of the general SWE-Agent suite. So you can do file search, you can edit code, you can have a command line. But there's one of the things I liked about this, a few kind of interactive tools that the agent can call, which you probably want for security scenarios, one of which is having a debugger. So there are just different tools that are like debug, kind of stateful tools is the way this is designed. I'll show you a different debugger design in a minute. Where the debugger says there's a command debugger start, debugger stop, debugger step. And those are just different top level commands that the agent can use. And also they're tools for connecting to servers. And again, these are implemented as three different tools that change the trajectory state. So the agent can ask to start a connection, stop a connection, or send a line. And the other thing that it kind of does a kind of a natural idea that you don't see very much is a lot of these, like if you need to like examine a binary file as part of digital forensics, like you're gonna run up your context length very quickly. So there is one like for long tool outputs, there is this kind of natural thing where, oh, let me just ask an LLM to summarize this long output. And then there are one thing which is kind of like a useful trick for when you're designing your own agents is, well, the first thing is always look at the trajectories, right? It's just like when you're doing regular supervised learning, or evaluation, always look at the data, right? So here it's like always look at the trajectories, right? You want to see what mistakes the agent's making and use that to design the harness. So like, one thing that's here is like there are kind of bullet points in the system instruction that says, oh yeah, I noticed the agent screwed up on this. Let me add a bullet point that says, please don't screw up in this way. And then it makes that error less often. Okay, so this had okay, let me so this is then kind of agent kind of versus on the left versus no agent on the right. And we see overall you kind of a similar set of increase that you saw from like the initial SWE-Agent results, like going from basically nothing is solved, like 3 to 4%, to like double-digit percentage. So it's kind of nice when you see so it seems like maybe this is the same thing as a SWE-Bench kind of leaderboard, but at a different point in the curve. Okay, so that's basically what I wanted to say about more general capture the flag challenges. So I wanted to end by talking about a kind of specific security task, which is kind of vulnerability detection. So so these would be like, if you want to exploit a computer system to get, unauthorized access or something like that. One way you could do this is by targeting bugs, right? In this kind of software, hardware, network layer, whatever. So I'm going to talk specifically about so a vulnerability is basically a bug in the system that has security implications. So I'm going to talk specifically about software vulnerabilities, both because I'm talking about coding agents and because that's, I think, where most of the work has happened so far. So some examples like, reading out of bounds or kind of cross-site scripting or something like that, where there's it could be potentially a small bug in the program that the attacker can use to do bad things. So so let me take an example of like an out of bounds write, which is kind of a particularly bad could have. So there is a kind of taxonomy of these different kind of software bugs that you can go to. And if you go to the taxonomy and say, okay, what kind of bug is it out of bounds right? It'll show you C code that looks like the code on the right, where it says, oh, okay, like one kind of illustrative version of this bug is, oh, if you have a function that returns -1 on error, and then I use that as an index, well, the -1 is going to get cast to, it could get cast to something unsigned, which is now going to point someplace way off into oblivion, and then you'll kind of write something to memory you didn't want to. And then when you look at that, it really seems like detecting vulnerabilities should be pretty easy, right? Because you just want to kind of find this data flow and find things that aren't within the bounds. So here's another example of an out of bounds, right? So this is an example of a kind of function from the Linux kernel. I mean, I know the first example was probably relatively simple. You might have seen the bug right away. I don't know, do you see the bug in this one? That's a joke. So, so what this is, I mean, actually, it's not like, I mean, it's too small for you to see, but this part of it isn't like, if you kind of make reasonable assumptions about Linux kernel macros, this part of this code is not that difficult to understand. So, what's happening here is this function is copying some data from a network packet. If you look at the two arguments to, I don't know what, I guess RCV stands for receive, but the first argument is the actual packet. The second argument is a header. And what it is doing is on, I have it in my notes. This line here, it's doing a malloc. The size is this thing's size, which it's pulling from the header. And then on line, let me see, it's 40, oh yeah, 44, I think. It's like it's doing a mem copy from something in the packet to this thing that's allocated based on the size. So what you can see here is that both of these things were read from the network, and there hasn't been checking done of the size. So that means that, oh, you could actually, there's no, the actual payload might not match the size in the header. And so if it doesn't, then the buffer that's allocated will be too small, and who knows how much you're going to be writing. So the reason so this is actually kind of a real vulnerability in the kernel. And the two things that I wanted to point out why this is hard, one is a bit of a needle in a haystack, right? There's going to be lots of functions like this in the Linux kernel, and it could be kind of difficult to craft inputs that reach them. I have to know which network protocol this thing is handling and so on. And so this kind of, identifying the actual data flow that breaks is fairly simple, but kind of identifying it from a lot of things that look similar but are perfectly safe is very difficult. And the second thing is this function on its own, it's not vulnerable or non-vulnerable. That's not even a well-defined question to say, is this function vulnerable? Because if the caller did the bounds checking, this function would be fine, right? So you actually can't understand whether this function is vulnerable or not without kind of knowing globally what's going on. Okay, so that's why AI for vulnerability detection is hard. In fact, this slide is basically a criticism of the next slide. So the next slide is, so we have this really nice source of data, which is the kind of vulnerability database. So there is a place where if you have public software and you discover a vulnerability, you can kind of get a unique tracking number, write a description, and give links to the patch, any other information about the advisories. And there are kind of thousands of these collected. So this seems like great for machine learning, right? Because all I need to do is say, oh, let me kind of download all of these vulnerabilities, and I'll kind of the patches, and I'll try to have some classifier that says whether things are vulnerable or not. So I'm exaggerating my criticism of this, but it's a very natural thing to do, right? The first thing you see a big data set on the web is let's download and use it. It's what you should do. And so there's a bunch of authors who have done this and kind of created data sets that say, oh, that the idea is that I'll take examples of code where we found a vulnerability, we've not found a vulnerability, and try to have, you can measure kind of detection or patching kind of based on this. Seems like a natural thing to do. Unfortunately, it's what I would have done too when I got started, and there's problems with it. The first problem is like how much of the code you put in the input, right? Like we saw in the previous slide, if I just look at one function that's been patched, that might not be where I might not know just looking at that function whether there's a problem or not. Or just because if I take a function in the patch, that might not be, what does it mean for a line of code to be vulnerable, right? There's a line of code where an incorrect memory access happens, sure, but that line of code might be correct right? The part that's incorrect might be something upstream, did something wrong. So the patch might be very far from the line of code that crashed. So the idea, even of a line of code or a function being vulnerable, something I'd argue it's not a meaningful concept. Then the other thing, like if you want it, so there is a question of like, how much context do you want to give? And I'm not, it's a very difficult question to answer. Or another question, how do you handle tangled commits? So I kind of mentioned this a little bit in SWE-Bench, like if you want to use this as a patching data set, well, lots of times a patch will do more than just fix the vulnerability. That's a very common case. So kind of learning from kind of difficult. The other thing is like, maybe this is easier, like kind of judging correctness of patches is kind of tricky, is like, if you can run the code, you could probably judge correctness. If you're trying to do it statically, then that's difficult, right? Because there are many ways to patch a vulnerability. And the fact I gave you this example of a vulnerability description, like these are vague. They will give you some information about where to start. They'll be vague, they'll be noisy, sometimes just because people are busy, they make mistakes, sometimes because you don't want to give out too much information about a security vulnerability. So I think these are really difficult issues. It's really difficult to come up with a static evaluation of vulnerability detection in this way. And I think these issues are fundamental. I think people have done a lot of great work trying to get around them to make the data sets cleaner and cleaner, but I think these data sets are really hard to use. So what I would recommend instead for working on this kind of problem is do something dynamic. So you need something like a SWE-Bench eval where you can actually run the code on an input that exposes the vulnerability. So there are some data sets. I left one out. That's one of the things you're supposed to ask me about. So I'll just tell you about it now. So there is like a DARPA sponsored competition going on now. The finals are later this year for like AI-based vulnerability detection. There was kind of an older one, 2016. It's also kind of interesting both because you can get the kind of programs and also I think the story of it is interesting if you want to look it up. There is a more recent security evaluation from Meta that contains some, it tests various parts of security for AI and AI for security, but there is like a memory vulnerability thing. There is a more recent thing that I like, which I forgot to put on the slide, which is ARVO. It's for some past vulnerabilities that have been found by fuzzers, containerized so that you can run them. So you can act checking of whether you found or fixed a so there is, I'm about to talk about one more agent, I promise. But there is a huge amount of research on automated techniques for vulnerability detection, like both some AI, but also kind of non-AI. So probably the most commonly used technique for automatically finding vulnerabilities is called fuzzing. So that is like you run the programs on many, many random inputs. You can choose them like a genetic algorithm type search. So you can flip bits in the inputs, you can mix and match them. And so you try to find an input that causes like a vulnerability to happen, like an out of bounds write. Those are really important in practice. Like security critical software is fuzzed extensively. So this is kind of important technology, but it also asymptotes. Like if you run a fuzzer for long enough on a software package, like you don't like continually find bugs even if they exist. And there are kind of famous examples of bugs where they've been found exploited in the wild. These are packages that are commonly fuzzed, but it was a difficult part of the code for the fuzzer to reach. There's a lot of work on, I think there's an opportunity for AI to try to, keep fuzzing things, but try to find deeper bugs, maybe that require kind of complex invariants that fuzzers can't reach. People work on static analysis for vulnerabilities, for vulnerability detection. It's kind of, there's a lot of interesting work that's been done in that space. The downside is kind of combinatorial explosion and the false positive rate. It's kind of it's very difficult to define. It's kind of a very, very difficult business to be in. And then like on some of these other data sets, I've talked about like, once you collect the vulnerability data sets on the previous slide, the ones that I don't like, you can try fine tuning an LLM on them. And so a lot of the papers that I cited will show you some results for that. But we wanted to do something different. So we thought there was kind of an opportunity to try to use um, to try to kind of, leverage AI in a more interesting way. And so that's this project that I'm involved in, which is called The Big Sleep. One thing I've noticed, having named a project this, is that most people do not have the same knowledge of classic cinema as I do. So The Big Sleep is kind of it's a famous movie from the 40s, but starring Humphrey Bogart. And if you like old movies, I recommend it. Um, the There's a story about why this is named that I won't get into. So this is a collaboration between some of us in Google DeepMind and some security experts from Google Project Zero. So these, this is a kind of a really a nice security group within Google that tries to find vulnerabilities. It does. They also succeed in kind of finding vulnerabilities in open source projects. And if you look at other things on their blog, you can see kind of how intense some of the vulnerabilities that they find are. So with this kind of group of collaborators, we've been kind of creating this agent. And the thing that motivated us about this was thinking about, or one way to motivate this is by thinking about kind of the experience of our collaborators in Project Zero as a human security researcher auditing code to try to find a vulnerability. They don't think of it like a classifier, right? You don't just read some code as a person, then say, yes, no, I think it's vulnerable, right? So instead, what you do is you read the code, try to understand it. You have some hypothesis about what would be going wrong, and then you try to run the code in a debugger or something, gain some information about whether your hypothesis is correct. And we wanted to see, and we think that if an AI is going to be successful, that it should do that too. So, and this kind of naturally suggested an agentic approach, where you'd have kind of a code browser and a debugger. So one way you can think about this is like analysis versus static. If you're trying to train just an LLM, maybe with some reasoning tokens or whatever to examine code, do some reasoning, come up with a vulnerability, that's kind of like static analysis. You haven't run the code. Whereas if you do an agentic approach, that's more like running a fuzzer. It's more like dynamic analysis. So we're focusing on a particular type of security issue in the Big Sleep, and that we're focusing on memory safety of vulnerabilities. And the idea is kind of given a code base, the goal of the agent is going to be like a fuzzer to generate an input that, when it's run on this program under test, causes bad memory behavior, like an out of bounds read or something. And what some of this is, so you get some of the advantages of a React style loop, but the other advantage compared to static analysis approaches, and even compared to, say, something like code editing, is in some ways, this is a simpler problem than code editing. And the reason is we have an oracle. So if we can, so I mentioned sanitizers to you earlier in the lecture. So when we are running the program in this agent, we are going to run it in a sanitizer in a debugger. So the goal of the agent is to actually generate an input that causes the program to crash. And when it crashes, we know you found a security bug. So, whereas if you're doing code generation, you don't know what the true tests are. So you have some part at the end where you have to figure out, oh, which patch do I choose? Here, it's like, if you find a bug, you find a bug. And one thing that's nice about, well, let me actually say the agent before I start telling you about how good it is. So, so what we're going to do in Big Sleep, it's going to be a React style agent. The goal of the agent is to generate an input that triggers a sanitizer crash. We have access to 3 different types of tools. So one is like a code browser tool. So this would be kind of similar to what I said about AutoCodeRover, that we actually index the program. We know what all the identifiers are. So our tools are like the type of tools you do in IDE navigation. So like, given the name of a method, jump to definition, or we can also follow cross-references. Then in order to generate inputs, we do that using we don't actually ask the agent to generate text directly. We ask the agent to write a Python program that generates the input. And the reason we do that is, like, if you want to do a buffer overrun or something, we don't want the agent to have to generate 2048 A's. We'd rather generate a Python program that says A times A times, right? It's just simpler. So we tell the agent, please generate a Python program that writes a string to a particular variable. We send that string to standard input. And then we can run the target program in a debugger. So we've talked about the Enigma agent also had a debugger. The design of this tool is similar but a little bit different. Um, so in our tool right now, the agent doesn't call the debugger interactively. What it does is it can say, first it calls the Python interpreter to set up an input. And then when it calls the debugger, it just runs the whole program. And it can optionally specify a list of quote unquote breakpoints. So a breakpoint is a file line number and an expression optionally. And what it does is we tell the agent they're breakpoints, but they're really watch points. So we'll run the whole program without stopping. I mean, anyway, we'll run the whole program without stopping. And at the end, we tell the agent, here are the breakpoints that were hit, and here's the value of the expressions you asked me for. So this way, this gives the agent another way to check whether when it generates an input, whether it's doing what it expects, whether it's having the control flow that the agent expects from the input. Okay, so let me show you an example of a trajectory. So I don't know what that meant. So this is let me see if this is an example of a program from the Meta CyberSec eval benchmark that I kind of briefly mentioned in the previous slide. So there is a system instruction that I haven't told you that kind of explains the task to the agent, describes the tools, and presents a problem-solving strategy and some guidelines to the agent. So the first thing the agent's going to do is say, okay, please show me the main method. So here, all of as I said, the control flow is completely dynamic, like React style, and there's no, the agent has to use the code browser tools to see the code. So then it gets a thing of the main method. And typically what the agent does is it summarizes the code, sometimes longer, sometimes less whenever it sees it. And then it'll decide, okay, I see an identifier there. Okay, you can't see there's a reader class because I snipped it out, but somewhere in this, there's a class called reader. So the agent says, okay, let me look at the reader class. And so it says, okay, let me look. So it looks at this, and it'll do a bunch of turns of code browsing. And after a while, the agent gets tired of code browsing, and it decides, okay, I think I found a vulnerability now. So what it does then, what we've instructed it to do, is to write a report that explains what the vulnerability is and what happens, how to exploit it. So the agent will generate this text after it's seen enough code where it says, oh, on line 70, you use string copy, but you didn't use bound checking. So if I create an input of this type, then this is, it loves saying a typical buffer overflow or a classic buffer overflow. It really likes that. So this could be exploited in this way. Here's my report. Now let me generate an input. And so the input is going to be some Python. Now this is a Python code. Here's an example of like what I said, where you can construct a long input. The agent can, it's helpful to have access to the library because, if you want to kind of generate, sorry, I'm having English. If you wanted the agent to generate binary strings, for example, can call, number to bytes. It can also, if it knows things about particular input formats. So if you have a program that takes JSON or images, has input, then the Python program can generate that. So in this case, after it generates some Python input, it calls the debugger function. It says, oh, these were like two errors that it thought was related to the vulnerable code path. So it says, oh yeah, please show me those. And so now we run the program in the debugger, and the agent is sad because the program exited without crashing. Generally, that's what you want, but not if you're doing a security audit. So now the agent's like, oh, okay, it didn't trigger the bug that it thought it did, so it can let's keep iterating. And so then it writes some things about why it messed up. So here it says, oh, the program failed earlier than anticipated because I forgot to do such and such. And so let me update the input so that I don't make this mistake. And it might iterate through, do that multiple times, and run the debugger again after each one. And then at some point it says, oh, the program crashes. Yay, it crashed. And then it gives some information, and then that means the agent has succeeded. So where are we right now? So I'd say the current kind of state of the agent is like we have kind of ways of testing it on kind of capture the flag challenges, like for example, this open L2 benchmark. And there it's kind of reasonably effective. There's still a lot that we need to do to scale it up. And we have found one real world vulnerability that we've disclosed, and that is kind of in SQLite. One thing about this, it's kind of one of the advantages of agents for this type of security task is you can put any information that you have in the context. So in this case, we did a type of variant analysis. So it turns out that when you find a security bug, a vulnerability in a project, there are often many similar vulnerabilities at different places in the same project. So those are called variants. And some, like a very large number of vulnerabilities that we see exploited in the wild are variants of bugs that have already been fixed. So what we did here is we took kind of a recent bug that had been fixed in SQLite, and we added the information about it into the context, and then said, I don't know, try to find something similar. And eventually, and it did. One thing I want to comment on this is one thing that was kind of working in our favor. This is maybe like a best case in some sense, because I mentioned the kind of Little Red Riding Hood principle. The agent has seen a lot of SQL queries, right, in the pre-training data. So if it sees kind of one SQL query that used to break the system, it's kind of easy for it. It's kind of reasonable that that LLM could generate similar queries. And the other thing I mentioned, fuzzing, it turns out we did go back with general purpose fuzzers and try to see, okay, now that we know where the bug is, can I get a kind of state of the art general purpose fuzzer to find it? And in some reason it was pretty hard to find. Like after 150 hours, we weren't able to find it. So yeah, so that's kind of our status so far. So finally, let me pop up and say, so I had to summarize just the security part of the lecture. So I think this is kind of a wide open area. We're just getting started. There's a lot to be done. I think it's an exciting application area for AI because agentic techniques seem really natural here. You need to interact with servers. You need to run debuggers, and it's also kind of a really nice test bed for code understanding methods, right? That to find a security issue and to say, oh yeah, this is a software vulnerability, you've got to think really carefully about the corner cases that the developer maybe didn't think of, and you have to track kind of data flow along stretches of the program. So it kind of, and if you're doing network or system security, you have to do that across multiple interacting programs in a system. So it really does require you to kind of understand at a deep level what programs are doing, which makes it kind of an interesting challenge task for LLMs. And, I've talked, in depth about some capture the flag stuff and some vulnerabilities, but there's kind of a huge space here that we're kind of only starting to get into. And there's a lot of real and this is the time we're starting to scale it up. So it's kind of an exciting time to be part of this area. Okay, so that's kind of all I have to say. I'm kind of happy to take some more questions. Thank you.